Right, for our next presenter, we have Michele Tartaglia. And she'll be presenting on groundwater pollution potential in Pinal County, Arizona, using the DRASTIC methodology. Michele?
Good evening, everyone. Like Iris said, my name is Michele Tartaglia, and I'll be presenting today on groundwater pollution potential in Pinal County, Arizona, using DRASTIC methodology. Pinal County is located in southern Arizona between Phoenix and Tucson. It is home to approximately 400,000 residents. Primary land uses include irrigated farmland with mostly uninhabited desert in the northeastern mountains. There are also several copper mines, manufacturing facilities, and grazing fields for sheep, cattle, and horses. If you drove down from Phoenix today, you probably drove through Pinal County on the I-10 highway. There are also two main rivers in the county, the Gila River and the San Pedro River, as well as a couple of reservoirs, including the San Carlos Reservoir in the northeast. Groundwater pollution is a serious issue for any agriculturally based economy, but even more so for an agriculture in the desert. Irrigation can exacerbate the issue by becoming the medium to which pesticides and nutrient runoff find their way into the groundwater, and possibly even the drinking water of Pinal's residents. It is important that land be classified by its contamination potential before any commercial or agricultural development begins. My early research was spurred by the question, which areas of Pinal County, Arizona are most susceptible to groundwater pollution? After I discovered the DRASTIC methodology for land assessment, I developed three objectives. First, to collect 7 layers of hydrogeologic data. Second, to prepare this data for the DRASTIC index system via GIS technology. And third, to assess the potential for groundwater pollution in Pinal County, Arizona. I'd like to give you a quick overview before we get started. I'll begin with the background of the DRASTIC methodology and continue into data collection and preparation, followed by the application of the DRASTIC index and a description of the 2 weighting systems. Then I'll end it with the analysis results, and I'll open for questions. The DRASTIC method was developed by the Environmental Protection Agency in 1987 as a standardized evaluation system to assess land for contamination vulnerability. Each letter of the acronym DRASTIC stands for a different hydrogeologic parameter needed for the assessment. D stands for depth to water, R for net recharge, A for aquifer media, S for soil media, T for topography, I for impact of the vadose, and C for hydraulic conductivity. These 7 layers are collected as raster shapefiles that have values for every pixel of land it represents. Each of the 7 components are assigned a numerical rating based on a given ranking system for the parameter. Then they are entered into the equation seen here to achieve a final index score. The rating of the depth to water layer is multiplied by the weighting of the depth to water layer, added to the rating of the net recharge, and so on and so on. For those of you who are not familiar with the raster calculations, here are some examples. If you add 2 rasters together, you are adding together the pixels that occupy the same geographic location. So if you're adding these 2 together, 1 plus 5 equals 6, 2 plus 6 equals 8, and so on. The same rule applies for multiplying rasters. Okay, on to the data. The first layer I retrieved was the depth to water layer, which I got from the USGS groundwater site inventory. To prepare this data, I selected only those wells tested for water table depth between the years 2000 and 2013, and between the months of October to February, when the water table will be its highest during the cold temperatures. This was the first map I came up with. The wells are color-coded by depth. Shallower wells in yellow could be seen along the San Pedro River, while there are deeper red wells to the western portion of Pinal. However, I still needed to convert this data into a raster format, so every pixel has a water table depth value. In order to do this, I used a kriging analysis. Kriging is a flexible interpolator that can create a predictive surface model. It is also an investigative tool that explores the cross-correlation and autocorrelation between points dependent on their distance between each other. I also had to reclassify the well depth values to the rating system of DRASTIC. So 0 to 5 feet would be a rating of 10, and 100 plus feet would be a rating of 1. This is the predictive surface that I created by kriging. Higher index values represent higher pollution vulnerability and are illustrated in darker colors. Both rivers and reservoirs are rated at a value of 10 since the depth to water to these locations is 0 feet. The next layer is net recharge. Recharge is the hydrologic process where water percolates downwards from surface water to groundwater. In Pinal County, higher levels of recharge are observed in mountainous catchment areas and irrigated cropland. My recharge data was retrieved from the USGS. The original data was a bit pixelated when I got it, so I used the polynomial approximation with exponential kernel algorithm to smooth it out. The data I used was in millimeters, but to rate it on the DRASTIC scale, I also had to convert it to inches. The first map I created for this was in millimeters per year for net recharge. As you can see, there's more recharge in the mountainous areas, as to be expected. However, I had to convert this to inches, and since all of Pinal County has net recharge of under 1 inch, my final raster for this was 1. The aquifer media layer is an underground layer of water-bearing permeable rock located under the vadose and topsoil layers. Unfortunately, I was unable to obtain current data for the aquifer layer, so I georeferenced it from previous DRASTIC report of Pinal County in 1992. This factor is not something that changes greatly over time, so these results are still accurate today. The different types of aquifer media are rated between ranges of shale, sandstone, limestone, gravel, etc. Georeferencing involves taking the original map seen here and choosing several points along the outline. I chose like 16 points at each corner and stretched it out to a known projected layer. I then digitized every polygon layer in the middle and achieved the final raster seen here. The darker aquifer media polygons indicate a rock type that is more easily permeated by water and has a higher susceptibility to groundwater pollution. Next, I retrieved the soil layer from the U.S. General Soil Map. I rated each soil type by its texture, clay, silt, sand, gravel, etc., and created the map seen here. The next layer I needed was topography, or slope. I downloaded this layer from the USGS National Map Viewer and ran it through a slope tool to calculate percentage slope. I then assigned the appropriate ratings and ended up with this map here. Higher slope is seen as less likely to be vulnerable to groundwater pollution, so there's lighter colors in the east where the mountains are and darker colors in the west. The next layer was the impact to the vadose. And the vadose is an unsaturated soil and rock class above the aquifer media. I also georeferenced this layer in the same way that I did with the aquifer media layer. The DRASTIC system rated this layer by ranges from silt, clay, shale, limestone, and so on. This was the original vadose map, and this was the map that I georeferenced from it. The last layer I needed was the hydraulic conductivity layer, which I also georeferenced. Hydraulic conductivity is measured in gallons per day of water that runs through the aquifer media divided by feet squared. This was the original map, and this was the map that I georeferenced. Now that I've collected all 7 layers that I need, I entered them into the DRASTIC equation. I've already rated all the layers, but there are 2 types of weighting systems that I can use. The standard weighting system and the agricultural weighting system. The standard weighting system is meant to be used on any type of land throughout the US, and the agricultural weighting system is naturally only for farmland and cropland areas. In the agricultural weighting system, it places more importance on soil media and topography than the standard system. This is how my equation looked in the raster calculator. It sounds kind of complicated, but in the end, once I got all my ratings together, it came together pretty well in the raster calculator. These are my final results for the standard weighted groundwater pollution potential for Pinal County. The darker colors indicate a high-risk area for groundwater pollution potential, and they're seen around rivers and reservoirs, but less so in the mountains. The agriculturally weighted map looks pretty similar. It's a bit more speckled because the topography layer was speckled, and that was given more weight in the agricultural weighting system. Here is agriculture in Pinal County, just to give you an idea where the crops are. And I placed the high-risk areas over the cropland to give you a good idea of where the high-risk areas that we need to look out for are. There are many overlapping high-risk areas and crops around the Gila and San Pedro River, but most of the crops do not intersect vulnerable land areas. So in conclusion, my original question, which areas of Pinal County, Arizona are most susceptible to groundwater pollution, were answered by my results. Pinal County, Arizona is most susceptible to groundwater pollution around water sources such as the Gila River and the San Pedro River. There is less pollution potential in the center of the county and around the mountainous northern region. Commercial and agricultural developers should be aware of these areas and can use the DRASTIC maps as a screening or planning resource. My further work will include publishing these results to ArcGIS Online and making them readily available to the residents of Pinal County, Arizona. And I'd be happy to take any questions you might have. Thank you.